The construction of houses according to these standards costs 5 divided by 15% more than the construction of conventional buildings, but they are preferred because they allow the owners to significantly save electricity. F-Energy is a standard for energy-efficient homes created in France. The F-Energy Association was established in 2006. This standard includes 3 main labels. BBC F-Energy, construction of low-energy houses, bâtiments basse consommation, BBC, energy consumption no more than 50 kilowatt-hours per square meter per year. F-Energy renovation, reconstruction of buildings, energy consumption up to 80 kWh/m superscript 2 per year. F-Energy Plus, the improved airtightness of the building reduces consumption by up to 40 kilowatt-hours per square meter per year. The passive house. A building designed according to strict energy efficiency criteria aimed at minimizing energy needs for heating and cooling. The zero-energy home. Evolution of the passive house, achieving a balance between energy consumption and production on an annual basis. A building designed to the passive house standard must provide excellent indoor air quality with reduced indoor pollutants and a constant flow of fresh air, reduced maintenance and operating costs, as well as drastically reduced energy consumption and CO2 emissions. An A-rated house is a low-energy house, BER methodology. A passive house is a house designed to have a heat consumption that is as low as is practically achievable. A low-carbon or zero-carbon house is a house that is responsible for little or no carbon emissions. The main criteria for building a passive house are: space heating requirement less than or equal to 15 kWh/m superscript 2. Heating load of the building less than or equal to 10 W/m superscript 2. Useful cooling demand less than or equal to 15 kWh/m superscript 2. Primary energy consumption less than or equal to 120 kWh/m superscript 2. Hermeticity of the building less than or equal to 0.6 AC/H superscript 1. Frequency of overheating less than or equal to 10%. In the construction of passive houses, 5 basic principles are applied, which guarantee high energy efficiency and living comfort. 5 basic requirements in the construction of passive houses. Thermal insulation with a maximum of 0.15 W/m superscript 2K. Passive house windows, the recommended U value for windows is 0.80 W/m superscript 2K, or less, with G values around 50%. Heat recovery ventilation, at least 75% of the heat from the exhaust air. Air tightness of the building. Absence of thermal bridges. The study of the single-family residential building in Smolyan, Bulgaria presents an interesting case for analyzing energy efficiency and potential improvements in the context of the specific climate of the region. The following aspects are key. Climatic conditions. Smolyan is located in a climate zone characterized by cold winters and cool summers. This imposes high requirements on the energy efficiency of buildings, especially in terms of heating during the winter months. As of January 11, 2018, the energy costs for 1 calendar year are as follows: for heating, 13,800 kWh, for DHW, 3,240 kWh, for household needs, 11,376 kWh. Energy consumption for 1 year, 186.21 kWh per square meter. With these data, the home falls into Energy Class B according to energy efficiency criteria. To reduce the consumption of electrical energy, at the end of 2018, a solar installation for domestic hot water, DHW, was installed on the roof of the building. This leads to a drop in electricity consumption by 1150 kW per year, the effect being mainly in the summer months. The disadvantages of the solar installation are high operating costs and complex maintenance. After installation of the solar domestic hot water system in 2018, there was a drop in energy consumption by almost 50% to 1,080 kWh per year. After the shutdown of the solar system for domestic hot water and the installation of the FEP at the beginning of 2021, there is a preservation of the consumed electric energy, 1,080 kWh per year, but also a sharp drop in the consumption of solid fuel from the heating water heating installation. 1 ton of wood pellets produces 4,600 kilowatts. The research and measurements made in this direction show that for 2021, nearly 700 kilograms of pellets or about 3,266 kilowatt-hours have been saved. The following data were received: for heating minus 10,534 kilowatt-hours, for DHW 1,080 kilowatt-hours, for household needs minus 2,661 kilowatt-hours. The heat pump heats DHW up to 50 degrees Celsius. The boiler's electric heater is also controlled by the heat pump unit. After reaching temp 50 C degree, the heater is turned on, which only reheats the water to 65 C degree. This system operation logic leads to a significant reduction in the energy consumption of the building. The conclusion that can be drawn based on the results of the implemented improvements is that the energy consumption has decreased by 7789 kWh in 1 calendar year. Thus, the energy consumption of the building has a value of 73.56 kWh per square meter for 1 year. The investigated building has a heat transfer coefficient of the external walls U equals 1.88 W/m2K. In order to fulfill the condition of regulation number 7, geolimestone wool 6 cm with a heat transfer coefficient U equals 0.035 W/m2K must be laid. As a result, a heat transfer coefficient of the external walls U equals 0.45 W/m2K will be achieved. The total heat losses for the heating season, kilowatt-hour, for an external wall with an area of 10 square meters in the Smolian region, where day degrees at 21 C degree equals 3,300 R. In conclusion, the detailed analysis of the building's energy consumption patterns, the profound impact of thermal insulation, and the efficiency of the heating system collectively underscore the building's exemplary performance in energy conservation. The building's classification into Energy Class A+ and its status as a near-zero energy building are testaments to its alignment with the highest standards of energy efficiency and environmental sustainability. This case study serves as a benchmark for future construction projects, emphasizing the critical role of energy-efficient design and technology in shaping sustainable and environmentally responsible buildings.